balance it.
Yeah. Piece of cake.
Piece of pie.
Why pie?
I like pie better.
Pie is superior to cake. No, it's not.
Oh.
All right, Sean.
Nope, Sean's number 3.
Oh, I'm sorry.
Go, Timmy.
Tim.
I had problems with two.
Except for
Like,
cheesecake.
I don't even know.
Strawberry.
And number 2, I thought I got it balanced, and I realized I didn't, and then
Probably somewhere a long oxidation number somewhere. We can always trace it back to that.
probably.
Is there supposed to be a half the microphone at one of those, like 1 half?
Easy on these.
It's a different
I think you
formula.
gotta
Let it
memorize
fool
are these general forms right here. Once you memorize those, it's easy. And you just gotta remember your nomenclature. Okay, acetic acid. Sodium carbonate. Ooh, acid plus carbonate forms.
Bomb.
Sodium acetate. Water and dioxide. Still need to balance that critter. Yes.
Well, he's usually really bad at balancing things.
It's a bird, it's a plane, it's chemistry man.
Did you give us like one of those variable formulas for the third one? Reaction with bases? Reaction with bases.
About what about it?
Like, you know how you gave us the HX plus M? Did you give us one of those?
Reaction with bases is HX plus M, OH equals MX plus H2O.
Oh yeah.
That's what I'll be talking about.
Good job, guys. Good job.
Give a hoo-ha. I'm actually feeling somewhat awake today. Sharp. Hoo-ha. Dude, that's a little scared.
Nah, I need 2 right there.
Got one more to teach you, and then we're gonna practice. Questions? 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 Going once.
Basically all about knowing nomenclature, right?
Not knowing nomenclature and knowing these general forms and being able to put the two together.
You're always alone. Okay. I love you.
Alright, I taught you 3 reactions yesterday. This is reaction number 4. We will call it dissociation in water. Acids dissociate. Ooh, there's a term from the past. Somebody remind me what that means.
Oh, Joe.
Someone remind me what that means.
That's where the water molecules break apart to solve.
Yeah, they separate. So the acid is the solute, and the water is the solvent, and the acid is dissociating in the water. All right? And we'll give that reaction this general form. HX is any acid. In water. And this is reversible, so we can set up an equilibrium with it to form like to draw a picture of this one, so let's draw a picture. Let's use a little particle model here. Haven't used our bingo chips in a while. HX. H2O.
I thought that was a C.
HX. Chips. Where are all my bingo chips?
It makes sense.
H2O. Now look what happens. How do we define an acid with our Bronsted-Lowry model? What do we define?
One or more hydrogens.
No, that's the Arrhenius model. A Bronsted-Lowry model, it was a blank donor, a proton donor. If you look at a hydrogen ion, let's draw a Bohr model of a hydrogen atom. Hydrogen is element number 1, right?
Yeah.
Which means it has how many protons?
Yeah.
We got 1 proton. Its atomic mass is what? 1. So it has no neutrons. And how many electrons does it have? 1. Alright? So that's a hydrogen atom. Now, if I turn it into a hydrogen ion, how do I turn it into a cation? What does it have to do? How is a positive ion? Pay attention. How is a positive ion formed? Take away the electron. What's left? Just a proton. So an acid is a proton donor. That's just basically a hydrogen nucleus, is what a proton is. So look what happens. We define an acid as a proton donor. Look what happens here. This acid donates a proton to the water molecule to make an H3O. This thing right here is what we call a hydronium ion. And that's going to be very, very important later. That's all this is. It just dissociates in water, and this is the way that it dissociates. When the acid breaks apart, that proton goes and attaches to a water molecule, and it forms a hydronium ion, and it leaves the anion by itself. Let me give you a specific example. Let's look at the dissociation of hydrochloric acid in water. Again, it's reversible. Products will be H3O plus and Cl minus. Now these are in aqueous. Water's in the liquid state. This particular acid is in the gaseous state, but sometimes they're in the solid state or they're in different states. So we can write a K expression for this because it's a reversible equilibrium. What is K going to be here? And there may or may not be anything in the numerator or in the denominator. In this case, you've got. Now, that's called the acid dissociation constant. And the higher this acid dissociation constant is, the stronger the acid is. That's not pH. We haven't gotten into pH yet.